And if you want to now figure out what's the displacement, notice that if I were to, let's say, keep my collarbone fixed and I just start looking around, then my pupils are clearly translating around the space, right? Even though I'm just rotating my head. So if I estimate the rotation of your head, I should be able to additionally estimate how much your pupils have been transformed, assuming that you kept your torso fixed. Say your collarbone was screwed down, let's suppose, and I should be able to estimate, make a reasonable average human being model of how much translation occurred. And that will get you pretty far. That's better than just assuming that your eyeballs are individually just rotating in place, right? Really, it's your head that's turning. So this is a very helpful approximation to try to compensate for some of the position change. But if the user decides to go back and forth like this, and you might remember one of the motion cues called parallax, where you see nearby objects moving at a faster rate than far away objects. If you'd like to do these kinds of motions and it doesn't work for you because you're not tracking the position back and forth, then it ends up being uncomfortable. So that causes motivation to bring in more sensors, right? So if you want to estimate position, what more do we need is the question, in addition to orientation. Again, you can fake some of the position. You might look at this. This is the greatest hope. So if you've just studied purely in textbooks, you may say, well, I figured out how to separate up from linear acceleration of the body. Why don't I just take this linear acceleration component, and instead of throwing it away, why don't I just integrate it once, I get velocity, integrate it twice, and I get position. So I can just figure out what your position is from that, right? Any difficulties with that? Let me explain some difficulties with that, and this will motivate why one might want to use cameras and other more sophisticated sensors. So if we just take this residual acceleration here left over after we got rid of the up component, first of all, we might have separated these two incorrectly. Another thing that might happen is, remember that we're always trying to estimate the orientation, and so if we have some errors in the estimation of the orientation, then we will not know exactly which way up is when we do the subtraction of up to get this residual component. So that will lead to some additional error that doesn't look like noise, it just looks like an offset, because we don't know truly which way up is. We cannot estimate the global frame perfectly, so that's going to cause additional errors. And now, suppose you have a small amount of errors. Say it's some kind of bias, like maybe 0.2 meters per second squared. Some amount that's left over here, and now you integrate that once, integrate it twice, and you take a look at how far your estimate is from reality after 5 or 10 seconds. It turns out this grows very fast. You may remember that when you integrate a constant once, you get a linear rate, and that's what happens. You get a linear drift rate that looks very much like the gyro drift rate. But if you integrate twice to get up to position, you're two derivatives away, right, or two integrals away from the position. Then it ends up with a fast quadratic growth rate. A simple offset like this, a simple fixed error, will cause a quadratic growth rate. So it's very much as if your head has a fictitious rocket thruster attached to it that's thrusting at this rate, and it makes you shoot away. And so that's what gets very, very bad about this. And if you think you can compensate for this perfectly, then there's still the problem of double integrating noise, which will also be a very fast drift rate. But this quadratic term tends to dominate, because usually we have a very simple kind of bias or offset here, because we can't accurately estimate the orientation, and we cannot perfectly calibrate the accelerometer. So these are the difficulties we get into. And so we did a lot of experiments trying to do whatever we could, also adding kinematic constraints based on the human body, trying to rule out absurd possibilities that would cause a faraway drift, because we know that your head's not detaching and floating away into space. However, it doesn't take long, like maybe a half a second or less, for a very large amount of drift error to occur, and then you cannot correct that very naturally. You have to detect it and correct it without making the person nauseated. So it ends up being very, very difficult. I think essentially impossible with this generation of sensing technology. And for the reasons I've explained, there are some fundamental limitations. No matter what, there's going to be some kind of bad drift unless you have some additional global reference for position, like a camera. Right? So that's what we're going to get to next. So that leads us to estimating position and orientation. So estimating position and orientation. So in other words, the full 6 degrees of freedom. Now this This acceleration information may very well be useful, this linear acceleration information. We can use this in a system to perform position and orientation tracking. However, we also want to have an extra signal that provides positional drift correction. All right. Couple of solutions. Well, possible general approaches. One is you could generate a non-constant magnetic or electromagnetic field. In other words, you may want to have some field lines that are intentionally bending, right? Or maybe you want the amplitude of the field to be intentionally changing in some way, and you've engineered a technology based on some base stations that you put around. So you may put a base station and there's some kind of field lines that you're generating from that base station, and based on that you may have a second base station as well if this doesn't provide enough information. So based on the information coming from one or more base stations, they could use ultra wideband radio as an EM example, or you could be generating magnetic fields. So based on the information obtained, when you place a sensor in here that's moving around and designed exactly to sense your non-constant vector fields, then it can recover the position. It's still, with this type of technology, it's still very hard to get a high degree of accuracy. It's very easy to warp magnetic fields by moving metal through the field, other kinds of problems like that. And the radio-based methods, I think, still cannot get down to the level of accuracy that we would like, which I should point out, the goal is sub-millimeter accuracy. Sub-millimeter accuracy. Why is the goal sub-millimeter accuracy? Well, if you have very large deviations, it's quite perceptible. You know, if I put on a virtual reality headset and I start seeing the world shaking and jittering, it becomes very perceptible. So what might be a reasonable tracking solution for looking at your hands, or just tracking viewpoint from a scene, but you're watching it on a screen, maybe up to 1 centimeter of error is fine, but we need to be sub-millimeter level of accuracy. It becomes very clear once you put on a virtual reality headset and you look at tracking errors that are a few millimeters or greater, you start to see the problems with it. So that's one thing I need to point out. We need to be extremely accurate. So this is one technology that has some hope, and there's certainly several companies developing methods and products in this arena, and there have been for many years. The other category, which I'll spend more time on, is visibility. Or another name for it is line of sight methods. And one of the most common implementations is based on cameras. So I can talk about various camera arrangements. And I believe I mentioned this last time. You could have human head wearing a headset and the camera is looking outward. So this is where the camera is on the headset. And this is often referred to in the industry as inside-out tracking. And the other case, you have the person again wearing the headset, and you have the camera out here. This is what you have in the lab on the Oculus Rift DK2s. And the camera is facing the user, and this is referred to as outside in, or I would put over here in-world camera. So either the camera's on the headset or the camera's in the world. Questions about that so far?
So what is the kind of marker that is being used? Like, is it an active marker or passive marker?
That's a very good question. That's exactly what I'm covering next. So, That's the thing to be asking. What is the camera going to be looking at, right? Yeah. So let me go over that. What does the camera need to see for this to work? We need to have line of sight or visibility towards something to make these methods work. It also helps to have an accurate model of how the camera projection works as well, right? How does the camera transform points that are in the world into image points? So that's the first thing I'll mention before completely answering your question is we have let's just make a simple pinhole camera model which uses perspective projection. So I have some features out in space. We'll just call them features, markers, features, whatever you like, out in space. You draw 3 of them here. And then imagine I have a camera that's pointed at these. So I have an image plane for the camera, like this. And then based on some projection model, I have all of these features treated as rays that all meet at a point somewhere using the perspective projection model. And so I want all these to come together at some particular point. And they pierce the image plane somewhere. If I can get the perspective right here. Probably not, but so I have some simple model of the imaging that looks like this, right? So I imagine there's an image plane, and you know, the particular coordinates of the points in this image plane, it might depend on where I stick this plane, and if I move the plane all the way past this focal point of the lines here, then the image will turn upside down. So let's suppose I have some model of the camera parameters so that I know where this plane is at, so that I can then understand based on this focal point here and where the points are, that for each one of these points that I see in the image, each one of these feature points that I see in the image, I know there is a corresponding ray in 3-dimensional space. Okay, and that's the thing, that's the assumption that I'm going to end up using, right? So when I see features in the image plane, I'm going to know that they lie on some particular ray based on how I've calibrated and set up the camera, right? So that's the model, and that's the information I'm going to be using. What exactly are these yellow stars I've drawn? That's what I want to talk about next, which I believe was the question that was just asked. So features, what are our choices? Well, we could use natural features. Right? And this is what I would call, let's say, hard computer vision. So imagine, for example, you have the inside-out camera, you have the camera on the headset, it just looks for whatever features it can find and works with those. It may, as the camera turns, it may grab some new features, and some that were previously in the field of view just fall out of the field of view, they disappear, that's fine. So it just robustly and automatically tries to use features however it can. So extract and maintain from natural scenes. This might not be such a bad room for this. As I look around, I see the walls have nice grid patterns on them. If I were to take the headset and look directly at with the camera and look directly at a perfectly white wall, there may be no features that I can use based on whatever feature detection algorithm I've made, right? We have to be careful about that. But it may be that for whatever automatic feature extraction and maintenance algorithm you've made, we may be able to find a natural scene that it might not work so well in. So if you're engineering a product, you have to think about that. Is it going to cover all the cases or not? Or is it going to cover enough of the cases that the users will not complain? Because if you get it wrong and you make gross errors in your estimate of your position, then this will have a dramatic effect in virtual reality because it may make people nauseated very quickly. You'll feel all of a sudden like you're moving when you're not. So very bad problem. One thing you have to pay attention to here, there are some tricks for doing this, but it may be possible to fool them as well. You have to remove any moving objects from the scene. So the headset may be moving, the camera may be on the headset and moving. You have to remove objects from the scene that you conclude are not moving just because the headset's moving. Now you have the gyro and accelerometer on the headset, so you may be able to figure out what motions are corresponding in the image plane. You may be able to figure out what motions correspond to your own motion and which motions are not explained by that, and then remove the ones that are not explained by that. So it's not bad. There's some information you can use there, but generally it's difficult. So I would say that overall, using current technology, the reliability is low. You'll see good demonstrations, but making this work very robustly in a very large number of settings and have sub-millimeter level accuracy, I haven't seen anything that can accomplish this yet. So this is kind of the state of the art. This is the state of the art for natural features. This then motivates people to go to artificial features. And I would call this, instead of hard computer vision, I would call this trivial computer vision. Because most of it boils down to something called blob detection as far as the vision part. Right? You're not doing very much work other than trying to identify markers that you've put into the environment. So it boils down to some kind of blob detection or variations of that, whatever patterns you've decided to put into the environment. You just have to go and quickly scan those back out of an image. So you're not really doing the type of computer vision research that would make your computer vision professors proud, let's say, right? This is more like vision in 1971 or something, computer vision, challenges of that era, let's say. So just simply pulling blobs out of an image, but you've designed it so that you have easy to find features. So some examples, you could use what are called QR tags. You could use what are called retroreflective markers. You could use LEDs. Laser projections. Some of these could be designed to work in the infrared spectrum so that they don't interfere with visible light, so that humans tend not to notice them, and there's not a kind of interference that may cause other troubles. So that's the choice you have. You have IR versus visible spectrum. Right, so that's the idea. Either you go the hard way or you go the easy way. When you go the easy way for artificial features, you end up with a more controlled environment and you can guarantee much more robust performance, right? It works in a larger variety of settings and with much higher accuracy. So that's one thing that we went with at Oculus on that stage for DK2 because of this high level of reliability and accuracy. It was better than trying to make the computer vision the most impressive computer vision ever, for example, right? So with a high level of robustness. This was very, very hard to achieve that. It would be more impressive if any of you can find a solution that works with natural features and has the same level of accuracy and robustness as this current DK2 tracker, for example, then I can assure you many companies would be very interested in that. So it's quite a difficult challenge. So let's take a look at kinds of markers. Let me say something about retroreflective markers. This is a very common technique that's used in motion capture systems. They've been around for quite a while. The motion picture industry has used them before for capturing dancers and digital actors, capturing real actors and turning them into digital actors, let's say. When you use retroreflective markers, the idea is you take the camera, and then around the camera you have a ring of lights. A ring of bright LEDs, right? So, there's lights facing me today, right? So you're trying to get a good image of me in the camera. So same thing, if you're trying to image something out here, shine some bright lights on it with LEDs, except we can move into the infrared spectrum so that the actor or artist who's moving around in these motion capture studios does not feel the interference or is not blinded by the lights. So you can make these infrared LEDs. So just exploit the fact that we can't see in that range. And then out here in the environment, you put the features, which are called retroreflective markers. Retroreflective markers. You can buy special paint and you can paint tiny objects. You may have seen what look like deer antlers sticking out of objects before in these kinds of systems, and you have gray tiny painted spheres. This is retroreflective paint. What will happen is that the amount of light coming back to the source, so if I shine a light, an IR light onto the source and then I look at the reflected light back, it will be independent of the angle at which the light hits this object. So there will tend to be a very bright spot coming back. So very nice for that. So that's retroreflective. It's as if you're shining into a mirror regardless of the orientation, which is a very unusual property, right? Normally, if you want to have the light bounce back at you, you have to have the mirror perfectly aligned. This is as if you have all orientations of mirrors when you shine the light. So it's guaranteed to come back and hit you very bright, hit the source very brightly. So this is one possibility. One of the things you have to pay attention to, though, is if you'd like to extend the range as much as possible of these sensors, then remember that the power of your light dissipates at a rate of 1 over d squared. I'll put 1 over distance squared. 1 over distance squared, right? So just usual power dissipation of a propagating wave in 3 dimensions. The amount of energy or power dissipation is 1 over the distance squared. And so the further away you move these, you get a lot of power up very close. The further away you move, the lower it gets. And you have to get the light to essentially travel twice the distance, right? It has to travel from the ring to the marker and then from the marker to the camera. So you have double the distance. So one possible improvement is to just put the light directly on the markers, right? If I can directly light the markers, I've cut the distance in half, right? So that means I should be able to move the markers further away and get the same amount of brightness in the camera. If I don't mind putting batteries or whatever I need, or this has to be plugged into a separate source. If it's on a headset, then I have to power these lights. So that's another alternative. That's what's used in the lab, which is I take the camera, and instead of having retroreflective markers, I have these special markers that I've designed, and these are just infrared LEDs. And we're also taking advantage of the fact of LEDs becoming increasingly more powerful and low cost, and very compact as well. Earlier LEDs were larger. They had a huge lens across them, so you could see them looking bright from different angles. Now they emit a much greater amount of light, infrared light in this case, very low cost, very small footprint. So now it's essentially, if you want to set up this visibility situation and think about the amount of power these LEDs have to have, you've cut it in half in order to be able to see them in the image with in the same way. And also, there's the efficiency of the retroreflective material, which I haven't covered as well. So this ends up being more efficient if you have the ability to power these markers. It's cheating even more, right? So in terms of computer vision, real computer vision, if you want to make something powerful, should be using natural features. If you put the features in the environment yourself as special markers that you've painted, you've cheated, right? You're helping the vision out, so that's fine. That gives much better performance, but not as impressive from a pure computer vision standpoint. You want to go even further, put some bright lights in the environment, bright and infrared in this case, and then just track those. And if they're small, very well separated, you get these points or these features that we need to get to the next level.